All right. Well, welcome to this pair distinguished lecture series. My name is Qingyan Chen. I am the director of the PolyU Academy for Interdisciplinary Research. So it's my great pleasure to introduce our today's distinguished speaker, Professor Michael GOODCHILD, who is a distinguished Professor Emeritus of Geography at the University of California, Santa Barbara. It's a very beautiful town, by the way. So Professor GOODCHILD is a close friend and a partner of PolyU. He is a senior fellow at the PAIR and the chairman of the International Advisory Committee of the Open Charitable Foundation Smart Cities Research Institute, which is led by Professor John Si. So previously, Professor GOODCHILD also served as the distinguished visiting chair professor of the Geographic Information Science at the Department of Land Surveying and Geoinformatics. Professor GOODCHILD is a global considered and the foremost expert in the field. His landmark paper in 1982 lays the foundation of GIS science, the science of collecting, analyzing, digesting, and using geographic data. In 2007, he coined the term frontiers geographic information. This concept describes an explosion of interest in using the web to create, assemble, and disseminate geographic information provided voluntarily by individuals. This really underpins the many modern applications like mobile apps, platforms, and systems that leverage user-generated geographical data and the Internet of Things for various purposes, from car navigation, road traffic management, town planning, to flood prevention, disaster outbreak management, biodiversity mapping, and many more. Professor GOODCHILD's outstanding contribution to GIS science is recognized by many honors. He was awarded the pretty fortunate, the Nobel Prize of Geography. I don't know if I pronounce that French name correctly. So it's the highest award in this subject in the world. So other awards include an honorary degree from the universities in Canada, the UK, the founders of the medal from the Royal Geographical Society, Lifetime Achievement Award from Geospatial Information and Technology Association, etc. He is also a member of the American Academy of the Arts and Science, and also a member of the U.S. National Academy of Sciences. That's really the highest honor in the United States as an engineer. So without further ado, ladies and gentlemen, please join me in welcoming Professor GOODCHILD.
Well, welcome, and thank you so much for that excellent introduction. And it's a great pleasure to be here and to be able to contribute to PAIR as a very important effort on the part of PolyU. I always enjoy coming here. I've been here many, many times, and particularly to work with PolyU and with Chinese University of Hong Kong and other universities in Hong Kong. I'd like to talk today under the title of Geospatial Futures. This is rather a miscellaneous collection because I believe that with an audience like this, it's important to find topics that anyone potentially can relate to. So you'll find it moving rapidly across the landscape of geospatial technology, which is an area that I've been closely associated with for now well over 50 years. It's a field that I have always found immensely satisfying, and for various reasons. And one time I wrote a paper on why I like this field. One of the most important, I think, is the constant connection between technology, and particularly high tech, and real world problems. And we see that every day, every time we use Google Maps for wayfinding. We use it all the time for buying and selling houses. There are all sorts of applications, which ensures that anyone working in this field is able to escape the ivory tower. It is able to be relevant and show the importance of their work constantly. So hopefully you'll get some sense of that as I go through this today. And the appropriate place to start, I think, is with a definition of geospatial, because that term is actually a neologism. It's a new word that only dates from the early 1990s and was invented at that time by the community of which I'm part to describe what they do. And it's become, I think, a very effective word to describe this field. In addition to that, the field has spent a lot of time over the years struggling with what to call itself. And early on, we called the field spatial data handling, which always annoyed me because it sounded like a parcel company. And we called the field spatial data infrastructure, which is still fairly current in Hong Kong, I have to say. But after almost 50 or more than 50 years, we began to realize that there was really only one 5-letter word that really summed it all up. And that's the word where. This is all about where. It's all about where things happen on the Earth's surface. So if you find geospatial a little too technical, a little too wordy, just go for where. It's a single syllable, which basically sums it up very beautifully. Right. So geospatial is about the space of the Earth's surface and also the near surface. And we might think of going up as far as 10 kilometers to the top of the atmosphere. And we might think of going down perhaps 10 kilometers into the solid Earth. We work at resolutions that are anything from 10 kilometers, which is about as coarse as you would want ever to use, all the way down to sub-meter. And so a huge range of spatial resolutions. And in terms of time, although unfortunately you would recognize quite quickly that this field has often ignored time, but insofar as we deal with time, we need to go back to the beginnings of geologic history and as far into the future as you like to go. So this is a pretty immense expanse of space and time, but it leaves out a lot. There are a lot of things that I would not call geospatial. So I want to talk about some of the key developments in this field. And in doing so, I'm looking both backwards and forwards. And I want to mention some of the things that have become legacy practices, things that we decided to do 50, 60 years ago that now turn out to be no longer making sense and, in fact, quite restrictive. So we'll have examples of places where the geospatial world thinks of itself in ways that really can only be explained from history, only be explained because they're what we always did. It was always the way we did it. And one of the key questions, and we might want to get into this later in discussion, is what is special about spatial? Why this concern for spatial? And we recognize a particular way of thinking, spatial thinking, which is actually on lists that people have made about the different ways in which humans think. We can talk about language thinking or visual thinking, but we should also talk about spatial thinking. This is a different way of thinking about the world. And we'll have some examples of that as we go through this. So I want to talk about new directions that are now emerging and talk about future prospects. What do we expect is going to happen in the future? So before I do that, though, I want to make an important distinction, which is one between spatial and what we increasingly call placial, another neologism, a word that was invented for a particular purpose. And what's going on here is that we have two entirely different ways of talking about where. The spatial way is to treat where as a measurement problem. It's to say that we have measuring instruments, more and more GPS, but earlier versions as well, as ways of measuring location. And because it's a measurement problem, it always has an accuracy issue. So it is impossible, for example, to measure location on the Earth's surface in absolute terms to much better than a meter. It's much easier to measure local distances, short distances, to much greater accuracy. But there is certainly always a limit to accuracy. And we'll have examples of that as we talk about this. There are also various ways of expressing those measurements. You can do it in latitude and longitude, degrees, minutes, and seconds. And once you get used to this field, you will know that the units digit in seconds, so for latitude it's 2, and for longitude it's 4, the units digit is worth about 30 meters on the Earth's surface. So because I've gone to one decimal place, you're looking at perhaps 3-meter accuracy for both latitude and longitude. That's too much for measuring the location of a house. It may be more appropriate measuring the location of a person. But my point is simply that however we do this, there will always be an accuracy issue because it's a measurement problem. And we could do it in terms of various grid systems. In North America, we often use the UTM system, where we would give coordinates of easting and northing, essentially doing the same thing, but in a different measurement system. And we might also compress this into a single code, combining both easting and northing. So there are many, as you go around the world, many different systems for expressing coordinates on the Earth's surface, all of them reflecting the fact that this is a measurement problem. However, the placial version is that geospatial is a naming problem, and that's something totally different. I doubt if there's any person in this room who could, from memory, specify the latitude and longitude of their current location. You might well go to GPS, but you can't do it from memory. We don't talk about latitude and longitude. But everybody in this room knows that they're at PolyU in HJ 303, which is a naming problem. So two very different approaches, the spatial and the placial. And increasingly, modern technology is consumed by conversions from one to the other. So when you ask Google Maps for directions, you might start with PolyU, a name. You might specify a name for your destination, but your problem is solved spatially. Your problem is solved by stringing together coordinates, not by stringing together names. So two very different ways, the way humans think, which is placial, and the way technology works, which is spatial. Through time, we've got more and more concerned about the placial. And I have to say that the placial was largely ignored in the early days of geospatial technology. But now it's become hugely important and a hugely important part of what we do. Here's another part of the naming process, which is that in 1507, in the small French town of Saint-Dié-des-Vosges, a gentleman by the name of Waldseemüller put together a map of the then known world. And he had this big chunk of the world that we now call South America, and he had to decide what to call it. So he made up a name. And he made it based on some letters that they'd received recently from Florence, from Amerigo Vespucci, And he decided to take Vespucci's first name and make it feminine. And so he stuck the name America on the map. And this is stuck. It's stuck for centuries now. And this is how things get named. We might talk about who these days has the right to do that. Very few people. The American president, of course, now thinks he has a right to change the names of things. But more generally, no, we have committees that have to approve names. But back in 1507, it was perfectly possible for Vautrin Lud and Martin Waldseemüller to stick that name on the map. Okay, the introduction already made reference to volunteer geographic information, or VGI. So it's something I became very concerned about back around 2007, when it became clear that the production of geographic information could involve not only governments, not only companies, but also individual citizens. And so this opened up a new era of the creation of geographic information using tools that everyone has access to. And so this is really a phenomenon of the 21st century. It's variously known as user-generated content or collective intelligence or crowdsourcing or asserted information. But essentially it amounts to the empowerment of millions of private citizens, largely untrained, no obvious reward, no guarantee that what they're doing is the truth, and no authority to do it. But nevertheless, having fun and putting together map information, which is disseminated through the internet and widely used. One of the first, well, here's a nice example of the sort of thing you see happening these days. This is someone who got interested in the geography of what you call a soft drink in a can. And so the different colors represent the choice between calling it pop, calling it Coke, calling it soda, calling it something else, irrespective of whether it's Coca-Cola or not. If you look at this map, you'll see some interesting things. California seems to be pretty much agreed. But you get enormous variation in the state of North Carolina or in Virginia. And so we can start asking questions. Perhaps more interestingly, we can ask where this data came from. And it looks like it's the result of about 120,000 people volunteering to a website as to what they call this stuff. You have some interesting patterns, like the pattern around St. Louis in Missouri, where they call it soda, unlike other people in Missouri, unlike other people in Illinois. So this is the sort of thing that's become possible to do in the past couple of decades. So a lot of this stuff started with a graduate student called Steve Coast at University College London in 2004, who said, if I want a digital map of the United Kingdom with all its streets and its rivers, the Ordnance Survey of Great Britain would charge me £3 million only to rent, not to purchase, and to rent for a year. So he said, this is ridiculous. Anybody with a GPS can go out, walk the streets of London, and make a map for nothing. And so that's what he set about doing. He got his friends together. He built an infrastructure. And today, this is OpenStreetMap, which is perhaps the biggest and most successful example of volunteer geographic information. And essentially, it's put the Ordnance Survey out of business in this area. This is much better quality than a lot of what is currently available. It's very interesting to look at this as a geographic problem and to ask questions like, why is it that in Germany there is so much denser information? The German OpenStreetMap pretty much has the size and shape of every house in Germany. Whereas in the United States, much of this stuff came from government sources. It was simply copied from free government sources. So a lot of interesting variation. This is very definitely a social movement, putting together a hugely complex pattern, free, widely available, in the form of OpenStreetMap. So if I were to go back to my first days in this field, they would be in May 1967, when I signed up for a two-week workshop at Harvard on what was then known as CIMAP, the first computer-based mapping package. It was incredibly crude. The only way you could get a map out of it was to use the line printer, which had a resolution of 1/8 of an inch by 1/10 of an inch. And you had to stand back, put this thing on the wall, and stand back about 20 feet to make much sense of it. And you can see the horrible things it does with things like the legend and the scale of the map. But we were hugely excited. Oh my God, we could use a computer to make maps. And so I signed up for this workshop largely because I couldn't see why you would want to do this. Computers at the time were about decoding messages. They were about sophisticated calculations. So why would you want to devote a computer to this kind of stuff? And try to make sense of that map of imagine having to find the location of your house on that map of Connecticut. So a lot of this got a big push from a gentleman called Roger Tomlinson, who I spent a lot of time working with in the late 80s, 90s, and who had a vision. And his vision was not so much about putting maps in computers, but about developing a computer application that would do many, many different things. He called this a geographic information system. And he argued that you could use this system to do many things. You could use it to make measurement from maps. What's so hard about that? Well, what's so hard about that is just try it. The only way you could measure area from a map back in those days was to overlay dots and count dots. And it was suggested at the time that this be a suitable application to be staffed by prisons. It was punishment, intensely labor intensive and very unreliable. So he said, put the map in a computer and then you can calculate the area very simply. Compiling maps. So when somebody makes a map using hand drawing, there are tasks like computing projections, which are actually very mathematical. He thought of remote sensing because increasingly in the 1960s, you started to get geographic information from Earth images from satellites. And he thought of landscape architecture because you could use the computer to create designs and to, in many ways, merge the aesthetic thinking of design with the technical thinking of GIS. So this was a vision in 1970, 1972. It caught on, and the geographic information system became a multi-billion-dollar industry by today. It was all based on a very simple idea that you could think of the world and the way the world looks as a series of layers. You could have data integrated into horizontal layers, maintaining a conceptual link to maps, but you could then stack those layers together to combine their contents. And this was basically the idea of GIS. And every time you open a textbook on GIS, one of the first things you're going to see is a stack of layers. But notice that that's not the only way you could slice things. You could slice it also vertically. And that's something geologists typically like to do when they're looking at cross sections. and you could slice it diagonally. And so there are many different ways in which you could slice the 3D cube. But that's one of the legacies that we have. We still, in GIS, think of the database as a collection, as a stack of layers. In 1965, computing, this is when Roger Tomlinson was starting to develop his vision, the state of computing was very primitive. There were no plotters. He persuaded the Canadian government to buy an entire IBM 360/65 at a cost of about $10 million at the time. And it had less memory than your smartphone. And it had a very limited hard disk. And essentially, all the data had to be stored on sequential tape. Think about how you would take the contents of a map and store them sequentially on a magnetic tape. And yet they did. He hired IBM, and they made the necessary software. There were other design decisions. So one very important design decision is that the source maps were assumed to be the truth. You were putting maps into a computer, it was assumed that what you were entering was the truth. So if your GIS was capable of regurgitating the map, it was perfect. The question of whether the map was actually representative of the world was completely irrelevant. And that, unfortunately, is still pretty much the way that the field thinks. We still think of the map as the truth, and we have great difficulty dealing with any uncertainty that may be present. And we'll have some examples of that before too long, excuse me. Another was that to get a map into a computer, the only thing they could think of doing was to scan it at high density. And so IBM actually built a scanner that was large enough to handle maps. And then you took the contents of that raster and you vectorized it to find the lines on the map. And you developed a data model, which was a very simple way of representing a map data set. One thing you did, though, was to flatten the Earth, because maps are flat. And so this idea, the idea of the Earth as a sphere, never really figured in 1965. And it wasn't until the mid-1990s that we really conquered the question of how to represent geographic data as a sphere rather than as a flat map. And the way we could do that in 1994 was to take a flat image and warp it onto a curved surface. And so this is something that became possible in the late 1980s. Silicon Graphics, IBM, had technology to do that. It would cost you $250,000 to buy a terminal which was capable of 3D display. But by 2005, when Google came out with Google Earth, it became possible to do it on a standard PC. So this is all a story of technology advancing and the legacy of the past preventing the adoption of new methods. So here's an example of the kind of world we get into. This is from, in fact, 1995, the SIGGRAPH exhibition, and the first demonstration of a GIS that used a globe instead of flat maps. The ball in the, here, is a very interesting device that you could spin to rotate the Earth on the screen. And you could zoom down. This is, of course, Japan, but you could zoom down to resolutions of as fine as a meter. This is actually a scene from a very interesting movie. It's a 4-part series made in Germany, and it is titled The $1 Billion Code. And if you ever get a chance to see it, it's on Netflix. You can easily access it. It's 4 episodes, and it gives you a wonderful view of the early history of GIS around that time. I actually appear in the movie because the basis of the movie is a lawsuit which German patent owners brought against Google. And I was Google's expert in defending Google's position. And so you will see me in the movie, except I'm not playing me. I'm being played by a rather attractive Australian young lady who provides the defense that I, in fact, provided. There's been a lot of history over the past 30 years of patents and lawsuits in this field. Here's one of the issues that, in fact, I've worked on. This is trying to represent the Earth not as a flattened Earth, but as a sphere, and do it in a way that is uniform across the sphere. What's happened here, this is an example of a discrete global grid, which is very much a research area. And this one is based on the octahedron. So if you take the North Pole and the South Pole and 4 points around the equator, you create an octahedron, 8 triangles. And then you can subdivide the triangles hierarchically into smaller and smaller and smaller pieces. And if you go down 16 layers, you get down to about 1 meter resolution. So you have, rather than flatten the Earth, you've created a representation of the Earth which is fully consistent with the fact that the Earth is close to a sphere. So a very interesting research field, some very interesting work done recently in China on a 3-dimensional version of this, where you can include the solid Earth as well as the Earth's surface. I want to give you a couple of examples of where this legacy of flattened maps impacts what we do with geospatial technology. This is an illustration from The Economist magazine, May 3rd, 2003. And it was illustrating an article about missiles from North Korea. And at that time, North Korea was talking about launching missiles with a range of 10,000 kilometers and 15,000 kilometers. And so The Economist simply took a flattened map and drew circles on it, which they thought were representative of 10,000 and 15,000 kilometers. Right? Now, hopefully you're starting to see what's going wrong here. Because what's going wrong is that the Earth isn't flat, and a circle is not the locus of points of equal distance on a distorted map. In fact, this is a Mercator projection, and on the Mercator projection, the poles are at infinity. They're not even on the map. And you may know, it's an interesting historic fact, that the French in the 18th century defined the meter as 1/10,000,000th of the distance from the equator to the pole. That's 10,000 kilometers. So in that way, the distance from the equator, typically Singapore, all the way to the pole is only 10,000 kilometers. So this is obviously very wrong. What amazes me about it is that this was put together by the editorial staff of The Economist magazine, who surely ought to know better, surely know that the Earth isn't flat. And 2 weeks later, The Economist published a correction, which shows that with a 10,000 kilometer missile, you can reach from Pyongyang all the way to pretty much to Chicago. It's a very different picture. So here's, I think, an excellent example of how the legacy of former practices impacts our ability to accommodate and make use of new technology. Here's another quick example. Here's the Earth, and again, it's projected. The North Pole is a strip right across the top, and the South Pole is a strip. We've turned points into strips. And I once took a flight from Dubai in the Persian Gulf to San Francisco on Emirates Airlines. The flight starts out from Dubai by going straight north. Right? And you're looking at this and say, whoa, San Francisco's over there. What are you doing that? And it's a 16, 17-hour flight, and it's important to stay awake, because at one point, when we get to the North Pole, the aircraft does an instantaneous turn to the left. And you can see this on the screen. And it's, well, nothing happened, we're just straight and level flight. And then seconds later, it does it again. And again, this is an artifact of trying to plot what is actually a great circle route on a projected map. Okay. So we are still, I think, in this field, in the business of escaping the legacy of past practice, whether it refers to the assumption that the map is always the truth, or the assumption that the Earth is flat. And every now and then, someone will make this kind of mistake because they don't have the basics of spatial thinking. They still expect circles to be loci of equal distance. Okay, let me switch now to GPS, and GPS has really revolutionized this whole field, and particularly an event in 2000 when Bill Clinton, as president, issued an executive order removing selective ability from GPS, selective availability. Up until that point, the full resolution, full accuracy of GPS was only available to the military. And this change of policy was precipitated, in fact, by the Second Gulf War, when it became clear that guys in the military were buying commercial GPS rather than try to compete for the few GPS receivers that were available from military sources. So all of a sudden, accuracy improved for civilians from about 100 meters to 10 meters. And that made a huge difference. All of the technology that we use today, the wayfinding, route guidance technology, all of it suddenly became possible. What became marginally possible also was the use of GPS for contact tracing, which of course was an important part of the response to COVID. Could you tell if two people were within 6 meters of each other? Probably not. 6 feet of each other. Probably not, because that was still better than the typical GPS story. These days we have other location measuring devices, some of which you may be less aware of than others. We all use RFID pretty much all the time. We may use Bluetooth, but I was unaware until quite recently of ALPR, which is automated license plate recognition. These are devices which read license plates. And the tricky thing is that they can be very small. They can be hidden in a traffic cone. Unlike CCTV, where you can usually see the device, these are much smaller. I came across them first because they show up in crime shows from the UK, because a car's license plate has been traced. And there are estimated to be over 100,000 ALPR sensors in the UK right now. So lots and lots and lots of interesting technology now for detecting location. Here's just a quick illustration of how good all of this has got. This is me using Google Maps to plot a route from my house up here down to a ballet performance at McCall Hall. And this is the kind of information, of course, that we work with all the time. What we may not recognize is the enormous amount of activity that goes on to create this. And the sophistication, because not only has Google recommended the what it thinks of as the best route, but it's also recommended alternatives which sacrifice time for distance or vice versa. So alternative routes which have to be significantly different from the route that. So a lot of this depends on VGI. It depends on the willingness of people to report changes. So the primary source of information about whether restaurants are still there is VGI. And a lot of the traffic information is also VGI. A little bit about the privacy problem, because the privacy problem persists. It's still a very significant problem. This is some interesting work by Andrew Curtis, who at the time was a faculty member at Louisiana State University, and was following up on Katrina and some of the deaths that occurred because of Hurricane Katrina. And the local newspaper published this image, which shows the approximate locations of each of the deaths from Katrina. And there was certainly a concern that that information should not be made public. But the thought was on the part of the newspaper that the accuracy wasn't sufficient to pin down specific houses. But the newspaper left in the outlines of the census tracts, which gave Andrew sufficient information to warp the newspaper image to a true map, and as a result, to actually determine where the death occurred in about 60 or 70% of the cases. So it's an illustration of how careless we can be given the accuracy and the availability of alternative sources, which can be combined to create much more accurate information. Here's where we currently, or this is 2018, but it's where we currently are. You may well have loaded apps onto your smartphone, and when you did so, you probably have not read all the way through the terms and conditions associated with the app. And so you may not know that some of the apps on your phone are actually reporting your location. They may be reporting the location only when the app is active, but in other cases, they may report it all the time. And this is some data obtained by the New York Times of one person's track. We know it's one person because even though the person's name has been stripped, the device ID is still there. So this is the result of stringing together all of the pings from one device over a period of a couple of months. There's 8,600 pings here. And it is now trivial, dead easy, to figure out who this person is, where this person works, where this person's boyfriend lives, where this person goes to see the doctor, which doctor the person goes to see, to expose all sorts of personal information about this person. All because the person didn't read through the terms and conditions, didn't turn off, disable this capability. So most recently, I think the number of companies that is specifically aggregating this kind of information from people running apps and reselling it for commercial purposes, the number of companies is now up around 100. And this is big business. And as soon as it's big business, the chance of shutting it down gets smaller and smaller. So Here's the person's house. This person, in fact, agreed to have their identity revealed. So if you go to the original article, you can find the person's name. Notice, however, that this is a single-family house. If this was a multifamily apartment building, this wouldn't be possible because you don't have sufficient resolution in the GPS. So it does target a particular kind of homeowner. Just to illustrate how difficult this can be, this is some work of a former student of mine, Luna Lee, looking at pings from Los Angeles. And you won't be able to see very clearly, but there are two sets of red dots around here and around here. These are all from one person's device. And if you wanted to figure out which house that person lived in, you'd have trouble because the pings straddle two houses, one under the tree and one here. And you would have trouble figuring out exactly what this person was doing up here. Maybe waiting for a bus, maybe having a coffee. But this is the kind of thing that's a consequence of the limited accuracy of GPS. My own sense is that I don't worry too much about this, because here's an example of me walking home from a sushi restaurant on the north side of Chicago to a hotel, and you look at the distortions that the GPS is subject to. This is all because, of course, the tall buildings in Chicago screen the GPS signal. So this is, yes, you can make the case that this is very threatening, but at the same time, it really is clunky against a lot of criteria. Okay, I'd like to perhaps finish with one very important story, which dates from 1854, and Dr. John Snow, who lived in London, and as a physician, was concerned about an outbreak of cholera that occurred in the Soho district, and was concerned about the lack of knowledge of how cholera was caused and how it was passed around. So he made this map. There's, of course, immediately a privacy issue, because today we wouldn't be able to distribute a map like that. And in the middle of the map here in Broad Street is a pump that he had his eye on because he wanted to investigate the possibility that it was water from that pump that transmitted cholera. And so based on the evidence that he collected, he did a lot of work on this. He decided that he was likely right and prevented access to the pump, and the cholera outbreak died out. So this is very important in the history of epidemiology. In fact, Snow is often known as the father of epidemiology. And this changed the whole perspective on public health, particularly in London, which up until this point had no running water and no sewage disposal. So here's a replica of the pump. It's outside the John Snow pub. And if you're ever in London, it's well worth visiting and going to the pub and drinking to the memory of John Snow and buying the t-shirt. And what he's trying to do is to sort out between four possible theories. And number one, the one that most people believed at the time, was that cholera was spread by bad air. And undoubtedly the air in that part of Soho was awful. Also contagion. This whole outbreak might have been passed by one individual who happened to locate in the center of the outbreak. Or a predisposed population. There might have been something about the people who lived in Soho that made them subject to cholera infection, or the water supply. Now, he was right. But you can argue that he was only right because he was able to turn this natural experiment into a controlled experiment. It was only by locking the pump that he was able to prove himself right. And the problem there is that these days, that kind of intervention is not just illegal, but it's also probably unethical. So this remains a very interesting and important. So he took control of the pump, and the principle here, which is a very important principle for anyone trying to do this kind of inference from geospatial data, is the principle of equifinality. There will always be many processes that can account for the same spatial pattern. I've given you 4. And one question you might want to think about is, if we adopted machine learning as the technology here, how would machine learning deal with alternative hypotheses? Because machine learning is mostly about confirming one hypothesis. And just to bring this totally up to date, here is Wuhan. And here are the early deaths that occurred from the COVID outbreak in Wuhan. And you can see that they're clustered around one point, which is the location of the market that many people believed was the source of the outbreak. So you can say this is a compelling illustration of the cause of the COVID outbreak. But you can also, along with the US Central Intelligence Agency, dispute that conclusion for the kinds of reasons that you might choose to dispute Snow's conclusions. So I'll leave it there. Thank you very much for your attention. I hope that was an interesting overview of many aspects of what, to me, is my research field, and a field that continues to excite me. So thank you for your attention.
Thank you very much, Professor Michael GOODCHILD. Thank you very much for your share the geospatial futures. I think we look back what in the past, then this, from a history of GIS, geoscience development, and also the future, what we can do with the geospatial. I think especially you mentioned about AI, what can be done by AI, what cannot, versus I think it's a very important issue to address on. So we have our floor open now. We invite our guests to raise questions if you have any. Yeah. And we also have a VIP from the University of Hong Kong, Professor Gong Peng, and Vice President of the university. Thank you for coming, and also waiting for your question.
Thank you very much, Mike. We are all your student. You know, this brings back a lot of memories. I started my study in Canada in 1986. 87, I went to Waterloo. But one of my colleagues who went to Canada with me, who went to study under Mike. And then later, Zhu Axing also went to study under Mike. So we often talk about his thoughts. And of course, later, we've been closely communicating. And thank you very much for this is already almost 40 years of help. You know, you obviously, your career added up another about 20 years. You know, we all know you started around in the late 1960s to in this profession. So it brings back a lot of memories, really. There are a couple of things I'd like to, I think everyone could think about. One thing I'd like you briefly update us. You know, in the 2009 or so, I invited you to, you and John Townshend, to look at our geoanalyst. You know, we call global analyst software
Yeah.
talking about the spherical distance, spherical overlay, map overlay for the analysis of bird fly and disease transmission. So after that, today you're also reminding us that the spherical distance, great arcs are mindful, which is an important 3D or a geo-villager, Earth villager should think about, not just, on plane, but also in 3D and spherical surfaces. I think it's important, more important today because of global change, climate change. People have so many larger scale demands on their study, analysis, teleconnection on Earth. They all need that kind of technique. But I actually have to excuse myself. I didn't really follow the technology afterwards, whether or not there are now, for example, in Israel, they already have this 3D based or spherical global analysis software, or somebody have done that. If you know that, I'd like you to share with us. First, I have another question.
Okay.
Thank you.
I think that this is a little bit like the question of uncertainty. I talked about how difficult it is to sell software that is honest about uncertainty because people want a single answer. And I think there's something similar here, that GIS has been marketed as a technology of the map, and the map is automatically flat. And so it has always been difficult for Esri to transform to a spherical perspective. And you can see that in the way in which they've handled their reaction to Google Earth, for example. They didn't wholeheartedly embrace. And one reason for that then is the map. You listen to Jack Dangermond, and he will talk a lot about the importance of the map. And I talked about the layer cake. And I could also talk about efforts funded by the National Science Foundation to promote what they call an Earth cube. And the problem with the Earth cube is, of course, that the Earth is flat under the cube. So I've thought a lot about an appropriate metaphor for a curved Earth. And I come up with the onion, because you can peel layers off the onion. And if I were illustrating this, I would talk about an exhibit that I once went to in Anchorage, Alaska, where the artist had produced approximately 50 globes, each with a different layer superimposed on it. But they were all 50 different, because there's no convenient metaphor, unlike the layers. So in that sense, our ability to think about a curved surface is actually limited. It's limited by the way we've always talked about GIS as a set of layers, as map-based. And so I'd cite it as another example of how the legacy of past practice becomes very difficult to escape.
Yeah, thank you very much.
A second.
May I? Yeah, this goes to modern. In the old days, map is an abstraction. It's a model about our environment.
Yeah.
Scale is an issue, local, regional, global. We are talking about, when spherical analysis is required, it is a global issue or large continental requirement. So now today, on the one would think that maps are symbolic synthesis about our knowledge on Earth. So there are lots of things that AI actually could actually learn.
Yeah.
But I don't really hear, lots of people play images. Even yesterday, there is a publication coming out from Google DeepMind that they produced a tool to do global mapping using their, large language model whatsoever combined. But I haven't really heard much or many on the map side. How map understanding, reading, and all of that, do you have any, experience recently follow you can share with us?
Yeah, and I think we are about to experience a tsunami because we are about to see Esri and other companies building foundation models of geospatial data. So instead of ChatGPT, which is essentially fed by the ability of companies like OpenAI to access vast repositories of text, the foundation models will access vast repositories of Earth images. And that raises, to me, some very interesting questions. So I'm very interested in agriculture and how vast data resources in agriculture will enable foundation models to be used by companies like Google, who will suggest that such a foundation model can answer any question about agriculture in the globe. And I came across a quotation from the head of Esri's Foundation Model Development Group in New Delhi, who said, "We have built a complete understanding of the world." That, to me, as a geographer, is immensely scary. It really doesn't use understanding in the way that we always used it in science. And it suggests all kinds of interesting questions. One question I would have, for example, has to do with the spatial extent of the training data for such a foundation model. I come from the state of Washington, and one obvious solution is to limit your spatial extent to the state of Washington and to train the foundation model on that data set. But the state of Washington has 240 commercial agricultural products. Should I therefore throw in data from the state of Illinois, where corn and soybeans dominate agriculture? By doing so, would I be severely biasing the training data? So the question of geographic bias becomes enormously important to the future of AI. And we need to be very clear about the value of expanding geographic extent in order to accumulate more data, at the same time as expanding geographic extent and running into spatial heterogeneity and therefore geographic bias. So I think that's a hugely important geographic question about the future of AI. And it's particularly poignant for weather forecasting and agriculture, which are the two fields that are really benefiting from foundation approaches to AI. Other fields, such as the urban field, are much more impeded by lack of data. We don't have vast resources of urban data that we could use to train models. And the same I would say about health, because certainly in the US, the vast majority of health data is in private hands. So I see data availability as a major driver in where AI is going in the next decade.
Thank you very much. Yeah. Do we have more questions from the floor? Oh, yes, that side, please. Yeah.
Yeah, thank you, Professor. And I believe nowadays GIS has been applied to all those areas like earth science and transportation. But I was wondering what kind of advances of technology in other areas can contribute to the future of GIS science?
Yeah, well, I think AI has to be the big one right now.
Yes.
We have gone through a series of short-lived enthusiasms, I have to say that, in the field over the past decade, dating from enthusiasm about big data with the 3 V's of velocity, velocity, volume, and no, I usually try to leave that one out. Anyway, it was a short-lived thing. We are also doing something similar with digital twins. And some of the ideas in digital twins are impacting GIS. So I would see the recent developments in GIS as fueling a number of interesting areas of development, all of which are driven by increasing availability of high-performance computing and increasing availability of data. Where that will lead us, heaven knows. The development of data centers is, I think, absolutely scary. The stories that are surfacing now about the vast amounts of cooling water that are being used and tapped by data centers, and the impact that has on people living near the data center. The noise of the data center, the traffic generated, and the use of energy, because data centers are driving up the cost of electricity to everybody. We survive well in the state of Washington because we have so much hydroelectricity. But there's a lot going to happen because of the implications of data center development on the availability of electric power, and also the storage of electric power and the distribution of electric power. So you don't have to go very far to see the ramifications of some of these developments. Largely without effective understanding of what the impacts are going to be.
Okay, thank you.
Thank you for the question. Any more questions? Oh, yes, that side.
Hello, Professor GOODCHILD. Thanks for your inspiring talk. I'm Richard Ma from LSJI. I have a quick question regarding the ethical issue in the future GIS research. As you have mentioned, that location is important, but it also may raise privacy issues. For example, the mobile phone data, trajectory data may expose people's information to the public. So I want to ask, do we need a specific ethical framework in the future general AI application, or we just use the nowadays ethical standard to that? Thank you.
So I'd make several points in response. The tradition in all of these technologies, not just GIS, but every other technology, has been that ethics is the responsibility of the user. The developers of the technology assume that it is beneficial to make the technology useful for as many purposes as possible, because that determines their sales. It determines the impact that their technology is going to have. But the result has been that it is almost entirely up to you and me to decide what is ethical and what is not. I like to think that that's actually not the only possible solution. I think that it would be entirely possible for the industry to develop software that takes some responsibility for ethical use by, not by effective fundamental redesign, but by flagging situations which are liable to lead to ethical issues. And one example I like to use is the ecological fallacy. So this is the fallacy that says, if you were to analyze data at the geographically aggregated level, so by census tract or by county or by province, and you were to find correlations, those correlations would apply only at the aggregate level. But the tendency for most people is to commit what is known as the ecological fallacy, which is to assume that that aggregate correlation also applies to the individual. So early analysis of COVID, for example, brought this home very clearly. People were discovering correlations between the incidence of COVID in areas such as census tracts and the socio-demographic factors in that tract. For example, the percentage of people who were below certain income levels, or the percentage of people who were immigrants. And those correlations then were written up as if they were individual. So as if being an immigrant made you more likely to be infected. That's a fallacy. It doesn't follow at all. What you have demonstrated is an aggregate relationship. So what I would love to see is, and it'd be very easy to do this, for the designer of the software to detect this emerging situation, detect that the user is looking at correlations at the aggregate level, and warn the user against committing an ecological fallacy. And it could just be a pop-up screen. And that pop-up screen could point to references, widely available background information. And all of this would help in a world in which we can no longer assume that every user of sophisticated software is aware of the potential ethical issues. Anybody these days can make a map. Anybody can find a correlation at the aggregate level. They don't need any kind of critical spatial thinking to do that. And we can never assume that everyone will be ethically sensitive. So let's make the software ethically sensitive. And certainly let's make it possible to turn off the pop-up. You've seen it once, you don't want to see it again. But I think that would start to shift the responsibility for ethical behavior from the user to the developer.
Thank you. We may have the last question.
Hello,
two,
Professor GOODCHILD. This is Joanne Fong from SGI Anomi, and I'm working in land survey and GIS field right now, and I'm an associate member of professional bodies. Refer to your slide, VGI, warranting geographic informations. I'm very interested about on it because actually there is a further technologies called blockchain. Do you have any opinion or maybe some studies on blockchain on GSI? And also, should we need any regulations for the informations for the reliability?
No, I don't. I'm very well aware that when the blockchain thing started, which I guess was about 20 years ago, maybe more, and there was a lot of talk about it. And I remember a conversation with a venture capitalist at the time who wanted to channel I don't know if you ever saw the movie The Graduate, but wanted to channel the scene in The Graduate where the young guy is advised by the old guy to think about plastics. That's where the future lies. And I remember this conversation saying, think about blockchain, it's where the future lies. But that hasn't happened, at least from my perspective. I'm aware that there's a lot of blockchain being used in areas like cryptocurrencies, but it's never intersected my interests sufficiently. So whether that's lurking in the wings, I don't know. We may be entering a period of blockchain. I don't know.
Okay, we have one more question from here.
Professor, my name is Greg. I have a philosophical question about ESG. So take, for example, in California, not too long ago, huge fire,
Yeah.
Society is destroyed, and you can actually predict that, governance didn't work. The fire comes, it's not a one-off thing, because every few years it comes back again.
Yeah.
And today with technology, pretty much you can see a lot, you can do a lot, you can avoid a lot if you have the right, foresight. Then you look at what happened in Texas, right? And I'm sure there's technology that you can actually pinpoint. But we're so far away, but we only hear the politics.
Yeah.
And politics meaning, it's not our fault. We didn't know about it. But how can it be possible these days? How can you not know about it? And that means if the environment is not there and the society is not there, then governance is completely missing. So ESG did not work for that case. So what is how would you see that argument going through?
Yeah, I've thought a lot about emergency response and about the role of information, and about why it is that in any emergency, it takes a substantial period of time for the information technology response to develop. And I could cite the Oklahoma City bombing of the 1990s or 9/11. All of these demonstrated how impossible it appears to be to prepare from an information technology perspective. And yet I think there are things we can do. So there are templates we could develop so that even though we never know exactly where and when an emergency is going to emerge, we can prepare for it much better than we do by developing the data models, the technology that can be rapidly populated. I think also volunteer geographic information is important. And one of the reasons I got very interested in VGI back around 2007 was because that was the era of Banda Aceh. If you remember the events in Indonesia, essentially the prevailing wisdom was that you have to wait until satellite data becomes available, because only then can you see the damage. And I thought, this is ridiculous, because you have millions of people on the ground, all of them perfectly capable of observing and recording the damage. And what you need is the ability to aggregate that information into some usable form. And so I was very excited when, after an election in Kenya, this technology emerged known as Ushahidi, which is a technology designed to allow citizens to assemble information using a very simple flip phone, not even a smartphone, because they're relying on placial descriptions of location. So you don't have to be able to measure GPS. And what you need is the ability to aggregate that information. And I thought it was remarkable that Tulane University in the US picked up Ushahidi and started to adapt it to the kinds of situations in the US, which we thought, oh, we've got all the technology in the world. Kenya's the one that needs technological advance. No. What we didn't have was technology designed for the kinds of popular use, because we always would rely on professional response. So I think there's a lot can be done. The whole VGI argument is that you have 7 billion people distributed over the planet, and all of them are perfectly equipped to acquire, record information. And what you need is the ability to aggregate it and distribute it.
Yeah, thank you. Last, Professor Chen, you have any question? No. Yeah, no more question, right? Yeah, perhaps I can quickly summarize the work, the talk today. The topic is the geospatial future. Then I see a lot of issues there. Our first of is data. We talk about data, which is the foundation for training AI models is future. We consider the extent of data and also qualitative data, which is very important to training AI models. We consider about spatial representation of the global, or even more beyond that. Professor Gong Peng mentioned about the representation of the world in the global way, sphere way. And I'm very glad you mentioned about Professor Dr. Jeff Dutton's work. I still remember after he graduated, he sent me his dissertation. Actually, he was the age of 60 by that. Yep. And then I sent a word back to him. I say, in our Chinese, we have a says, it's never too old to study. In Chinese, it's mean 活到老学到老. I translate that into English. I present that words to him. I think it's a very fundamental word. And also Professor GOODCHILD mentioned about from 2D and extend 3D. I think that's very important to represent not only the deep Earth, but the sphere and atmosphere. I think that's a very important modeling part of geospatial. One more important future, I would think, is about the AI and the world model, which link both with our geography study, and also physics, how we understand the real world and the extent of phenomena around the world. I think that's two things putting together and it helps the world model. And I would also think that's the part we can contribute to the future of AI, very important part. Starting from the computer vision and the language, and you mentioned about map, and that's word model. It's really understand the word behaviors and the physics behind that. I think that's the future, and also that's the part we can contribute as geospatial scientists or geoinformatics or geoscience. So once again, may I invite you to thank Professor Michael GOODCHILD for his presentation today, and very informative and insightful. Thank you.
Yeah. Well, also thank you, Professor Shi, for chairing this and giving the summary. Now, to express payers' appreciation to Professor GOODCHILD's presentation, we make a souvenir for you. Oh, yeah. This is specially made with your names and the title of your lecture wonderful. Today. So I also wanted to thank everyone coming here today for this lecture, and especially for those who ask questions to make this lecture even more interesting. So thank you again, and please tuned for our next distinguished lecture that will be in September. Okay, thank you very much, and it's adjourned.